All right, so what we've got on the board here is where work energy theorem and law of conservation of energy overlap. Okay? In order for there to be any energy to be conserved, work first has to be done, because work is what puts that mechanical energy into the system. Okay, so if we're looking at this situation here, okay, where we have a person who draws back a bow using 100 newtons of force, half a meter, okay, can I calculate how much work they've done? How much? 50 joules. Okay, force times distance. They used 100 newtons worth of force times a half a meter. Okay, what's the work done on the bow? 50 joules. Okay, how much potential energy is stored in the bow? 50 joules. Okay, how much kinetic energy does the arrow have when it's released from the bow? 50 joules. Okay, since this thing is being shot straight up in the air, what's the maximum potential energy of the arrow? 50 joules. Okay, so does everyone kind of follow here? You'd be surprised how often on a multiple choice question like that I get people. Okay, where I give them something simple like that and say, okay, what would the maximum potential energy be? And if I make one of the options impossible to calculate, you would be shocked how many people pick that one.
Oh, and they do like a bunch of impossible math to come up with randomness?
Well, there isn't usually too much randomness. It's like I'll put in the correct answer, 2 or 3 random numbers, and then impossible to calculate. And people look at that and they're like, I have no idea. It must be impossible. Okay, and they just pick must be impossible to calculate. Okay, when it's quite simple. If I do work, I put energy into a system. And because of the law of conservation of energy, that energy has to always be there. It can be converted into other forms. And in an isolated system like what we're dealing with here, that would mean all of it gets converted into potential energy in the bow. Okay, kinetic energy in the arrow, potential energy in the arrow later. Okay, all of that stuff. In the real world, is that what actually happens? No. If I do 50 joules worth of work drawing back a bow, there might only be about 45 joules actually stored in the arrow, or sorry, stored in the bow as potential energy. Because when you draw back a bow, can you hear it? Is sound a form of energy? Then there's some of your work. Okay? Some of your work gets turned into a wasted form of energy. Sound. Probably a little bit of heat too. Okay? Bending something generally causes a little bit of heat to happen. All right? So we would lose a little bit of energy there. Okay? When I release the bow, okay, does it make sound? So then a little bit more energy would be lost as sound. Okay? Not all of that 50 joules worth of work is going to end up in the arrow. All right? But we deal with isolated systems in this class where everything works the theoretically possible way, okay, where all the energy is conserved. In the real world, the energy is still conserved. It just doesn't all end up being mechanical. Okay? It becomes sound and heat and light and other forms of wasted energy that just go into the surroundings. Everybody okay with that? Okay? But because that's like really hard to calculate, we don't bother doing that in Science 10. Okay? We just deal with all the energy gets converted. It's 100% efficient, even though that's physically impossible. Okay? It's just easier to deal with that way. Okay, so everybody's okay with how this question worked? All right. Okay, we did those questions yesterday. All right, so law of conservation. Whoa. That'll make you seasick if you read that for too long. Okay. Because I guess when I scanned it, I didn't push the book down hard enough. It's a little curvy. Okay, so law of conservation of energy states that the total amount of energy in a given situation remains constant. Energy can't be created, it can't be destroyed. Okay, but it can be converted from one form to another. And for our purposes, that is always going to mean from potential to kinetic and kinetic to potential. Okay, always kind of flip-flopping into each other. All right, everybody okay with that idea? Okay, we're just going to be dealing with mechanical energy, which is kinetic, and gravitational potential energy. All right, so if I pick up a rock and I walk up to the top of a cliff, okay, and I hold the rock out over the edge, does the rock have mechanical energy? Okay, it does. All of it is in what form if I'm just holding it? All of it is potential. Okay, when it gets to the bottom, if I drop it, when it gets to the bottom, will it have the same amount of mechanical energy?
Yes.
Yes. All of it will be kinetic. Okay, that's the law of conservation of mechanical energy. And that is what's going on in this example here. Okay, so if I have a rock that's dropped over the edge of a cliff, okay, 30 meters above the surface of the lake, I should be able to calculate its speed when it hits the lake. Okay, here's why, and you'll want to write this down, kind of follow along. Okay, the law of conservation of mechanical energy says that my initial mechanical energy and my final mechanical energy are equal, because energy can't be created or destroyed. Yesterday, we learned how to calculate mechanical energy. Now, what two things do I add together to get mechanical energy?
Kinetic and potential.
Kinetic and potential. I only asked because you told me first thing this morning when it came in. Okay, so my initial mechanical energy would be my initial potential plus my initial kinetic. Would it have something similar on the other side of the equal sign? Okay, my final mechanical energy would be my final potential energy plus my final kinetic energy. Okay. Have I still written, have I written the same thing twice now? Yeah, I've just expanded it out. Okay, and in our work energy theorem problems, that was also what we did, right? We had W equals delta E. And then we went FD equals, you know, this minus this. We just kept making the equation bigger and bigger and bigger. That's what we're going to do here as well. Okay, now before I make this equation bigger, okay, I should probably look at the situation that I'm dealing with. Okay, if I'm holding a rock out over the edge of a cliff, you guys just told me it only has what kind of energy then? Okay, so what is my initial kinetic energy then?
0.
Okay, and I can get rid of that. Okay, and you guys told me a minute ago as well that when it hits the lake, all of its energy will be kinetic, because what will its height be then?
0.
Right? Okay, so it won't have any final potential either. Do I have formulas that calculate these two things?
Yep.
Okay. Am I still saying the same thing?
Yeah.
My initial mechanical energy, which is all potential, equals my final mechanical energy, which just happens to be all kinetic. Okay. Can I solve for V? I can. Okay. So what do I have to do with the half and the m? Okay, in this case, what happens to the m's? In this case, they cancel. Okay? Do anyone know why?
Because it's division.
Okay, because it's division, but also because of something that's important in how physics works.
Mass stays the same.
Well, mass is the same on both sides. That's the mathematical reasoning. The physical reasoning is this. All things in an isolated system fall at the same rate, regardless of their mass. It doesn't matter whether I drop a rock, a basketball, a beach ball, or a dump truck. They'll all be going the same speed when they get to the lake. Okay? If there's no air resistance, everything falls at the same rate of 9.81 meters per second squared. So your speed when you get to the bottom isn't dependent on your mass. Your energy is dependent on your mass, but I'm not being asked to calculate energy. I'm being asked to calculate speed, which is not dependent on my mass. Okay? So if you're comfortable with it in this situation, you can cancel mass. If you're not comfortable with it, you can leave it in there, and it won't make any difference. Okay? It'll calculate out the same. All right, so what I've got then is that GHI over 1/2 equals VF squared. I want just VF, so what do I have to do? Square root. Okay, so the square root of G times H initial over 1/2 equals VF. Okay, so for us, that's 9.81. How high was the cliff? 30 meters. Times 30, okay, divided by 1/2, square rooted. All right, so that rock will be going 24 meters, actually we have 3 significant digits, 24.3 meters per second. When it reaches reaches the ground. Now, just to show you that the mass makes no difference, okay, I'll do exactly the same thing, but I'll include the mass. 1.5 times 9.81 times 30, okay, divided by 1/2. Oh, sorry, divided by 1/2 times 1.5, okay, and then square root that. See, it's already the same number. And 588.6, square root that, and I still get 24.26. Okay, so if I'm looking for height or speed, mass isn't going to matter, right? If they're asking me calculate the final potential energy, then I have to have mass in there because I wouldn't get joules without it. Okay, I need to have kilogram meters squared per second squared. Okay, all right, so what we did there sort of makes sense. Okay, remember how we had to learn the pattern for all work energy theorem problems? Well, this is the pattern for all conservation of energy problems. Okay, you start out with EI equals EF. Okay, you put in your mechanical energy calculations, EP plus EK equals EP plus EK. You can eliminate any forms that are zero, then plug in the formulas, and then manipulate and solve. It's always the same pattern. Once you learn the pattern, you really can't go wrong. Okay? The trick is this. Work energy theorem problems and conservation of energy problems sound a lot alike when you read them because they give you similar kinds of information. Okay? In a work energy theorem problem, you might get a velocity, you might get a height. Okay? You're definitely going to get those in a conservation of energy problem. Okay? You're probably going to get a mass. But there's one thing you're never going to get in a conservation of energy problem that you'll always get, okay, or probably always get, in a work energy theorem problem, and that's force. Okay? If there's a force present, it's not a conservation of energy problem because forces do work. And work means energy changes. Okay? In this problem, we know the energy is not changing because there's no forces doing any work. Okay? So I have to look for that in the context of the question. Okay? Does the context of the question imply that there's work being done and that energy is changing? In a work energy theorem problem, you're only going to get velocities or heights. You're not going to get both. In this kind of question, you're going to get both. Okay? So those are the things to kind of watch for. It just takes a little bit of practice before you're like, oh, that's definitely a conservation of energy problem. That's definitely a work energy theorem problem. Okay? It just takes a little bit of practice. Okay. Oh, that's the one we just did. Okay. All right. See if you can try these two. They're just like what we just did. Okay? One is asking you for what? Number 11 is exactly like what we just did. And number 12 is asking you for a height instead of a speed. Okay, how do I know that the first one, number 11 there, is a conservation of energy question and not a work energy theorem question? There's no force, there's no distance, I don't see the word work, okay, in there anywhere, right? And I can tell that it's just an object falling, which means gravity is the only thing that's causing anything to happen, all right? So I'm going to say that for question number 1, the initial mechanical energy equals the final mechanical energy. Okay? And I'm going to say that that means the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Are any of those forms of energy zero? Which ones? Initial kinetic is 0 because I'm dropping it, and if anything is dropped, it's starting from rest, so it has no kinetic. Okay? And the other part is talking about the ground. How much potential energy do you have on the ground? 0. So my final potential energy is also 0. All right, that simplifies things. Now I can put in my formulas. M times G times H initial equals 1/2 mv final squared. Okay, I can cancel off the m's because it's on both sides. I'm trying to find VF, right? So I'm going to divide both sides by 1/2, and then I'm going to square root. Okay, so VF will be the square root of 9.81 times the initial height, which was 12 meters, okay, and then divided by 1/2, all square rooted, should give me 15.3. Okay, so 9.81 times 12, okay, divided by 0.5, square root that, okay, 15.3 meters per second. Okay, now, a 10 kilogram water balloon has how many liters of water in it? 10. Yeah, 1 liter of water, okay, is a kilogram of water.
I love
Not
the
counting
metric
the
system.
actual.
Not counting the balloon, yeah.
I
So,
love the metric system.
I wouldn't want to get hit by a 10 kilogram object even if it was a liquid, okay? That would hurt.
It's bad, that would be.
Yeah, well, like if it was a strong, balloon,
Actually,
it
I'd be
could
okay
hurt your
with
neck if it hit you.
I'd be okay with it if I'm laying on the ground because then most of the force would go into the ground.
You'd still be squished in between.
Maybe it's.
No,
You're not getting straight. Not going back and
The
forth.
thing's squishy though, so it'll squish before
Yeah,
I
like
squish.
the
thing-
balloon itself
the
will
neck
absorb
stress is
impact.
because, you know, it's already squished.
Okay, I'm gonna say this, please don't try that at home. Okay, yeah. Okay, how many people have done 12? Okay, do we need more time on 12? Okay, give you a few more minutes on 12 then. Okay, here's the thing you need to understand about number 12. I don't know if you guys have ever seen these trampolines that are ground level. You dig a hole out underneath them. Okay, so the child is at ground level, okay, when they are moving at 1.60 meters per second. We're looking for how high above the trampoline they're gonna go.
Where on the trampoline are they?
Right dead center.
That
so-
means they'll be dropped.
Nope,
lower
if
than
they're
the
dropped down, they have elastic potential energy. So the elastic potential energy has done work and they are ground level. Trampoline is completely flat. They are moving at 1.6 meters per second. Okay, which means they only have what kind of energy initial? Kinetic. They're at ground level, moving at 1.6 meters per second. So their initial on this one is kinetic. Okay, again, am I given force or distance, or is there any mention of work?
No.
Gravity is the only thing causing changes in this, right? Then it's a conservation of energy question. All right, so EI equals EF. Okay, initially on the trampoline at ground level, okay? EP initial plus EK initial equals EP final plus EK final. All right, so we established that initially we are at ground level, which means we don't have any of that. Okay, at their maximum height, how fast are they going? 0. That's where they turn around. Okay, so at their maximum height, they don't have any of this. So that can be canceled. Okay, there's no kinetic energy if you have no speed. So then we can say that 1/2 mvi squared equals m times g times h final. They want me to find h final, right? So I'm going to divide both sides by m times g. M's going to cancel, okay? And now I'm solving for hf. So we'll go 1/2 times 1.6 squared divided by 9.81. Okay, now sometimes people don't like this answer because it seems kind of small, and it is. Okay, so 0.5 times 1.6 squared divided by 9.81, okay, 13 centimeters. It's a little kid, okay? It's just like a little kid. So they weren't like, it wasn't like a big jump. They weren't doing backflips or anything, okay? So 0.13, okay? 0.13 meters. Okay, everybody all right with that? Making sense? Now, do you suppose they get a little more involved than this? Yeah, very rarely is it just going to be like EP initial equals EK final. Okay, you're going to run into some questions where maybe you have all 4 kinds. Okay, doesn't make it a whole lot harder. You just have a little bit more algebra to do. The principle is still the same. Okay. All right, now looking at this diagram here with the pulley and the 2 masses. Okay, so if I've got it in this position with the 2 kilogram mass higher than the 1 kilogram mass, is there energy in that system?
Yeah.
Okay, what kind? Potential. Which box has the potential energy?
The 2 kilograms.
Right. How come the 1 kilogram mass doesn't have any potential energy?
It's the one that has force active on it.
Right. It's not got any potential to fall. It's going to be pulled up. Okay? Now, when I let this thing go, is the whole system going to accelerate?
Yes.
Yes. So even though all the potential energy was in the 2 kilogram mass, when this thing is accelerating, okay, will all of the parts have kinetic energy?
Yes.
Yes. Okay? So does that mean though that the energy is still conserved?
Yes.
Yes. The total amount of energy in the system is going to be conserved. Okay? And the reason for that is these two things are both going to accelerate. They're both going to gain kinetic energy, but they're gaining it because the potential energy from the 2 kilogram mass is being converted into kinetic. Okay? But the total amount of energy has to remain the same. Otherwise, I'd be either creating energy or destroying it. That whole system's energy has to stay the same throughout. Okay? Now, the other thing to remember is when the 1 kilogram mass moves upwards, it's not only gaining kinetic, it's also gaining potential. Okay? Not really, because it can't really fall. Okay? It's attached to the 2 kilogram mass, and because of that, it can't really fall. So you can't have gravitational potential energy if there's no potential to fall. And there isn't. Okay? The only time it would have potential energy would be if it ran into the top of the pulley and broke the rope. Now it's no longer part of the system, and now its kinetic energy would be converted to potential and fall back down. Okay? That sort of makes sense? Okay. All right, we already talked about this problem, so we're going to skip off of that one. Okay. All right, I would like you guys to try number 14. Oh, thank you, Mr. Real. Now, on number 14, just going to do a quick demo here so you can kind of envision this. Okay, this is my ghetto physics demo. Okay, it comes out like, well, at least a double-digit amount of times per semester in Physics 20, okay? But it's also coming out here because it can be both a circular motion demonstration, okay, and it can also be a pendulum. I am saving taxpayer dollars left, right, and center, okay? Because this is a roll of athletic tape on the drawstring from my hoodie. Okay, this is what happens when you cut money from education, you get ghetto physics. Okay, but physics is physics, whether it's ghetto or not. So, okay, this is a pendulum. It's swinging back and forth, back and forth. Okay, the only way it gets started is if I do what? Work. Okay, I pull it to this position here and I give it what kind of energy? All right, once I let it go, it accelerates down, it converts it to kinetic, okay? And it'll just continue converting potential to kinetic, back and forth, okay, for as long as it'll swing.
Also helps that you're doing work with your arm there.
Yeah, I mean, I'm keeping it going, right? If I didn't do that, so I've stopped doing that. Okay, it's still going to swing for quite a while. A pendulum is pretty efficient through a narrow angle. Okay, everyone all right with that? Okay, so on that one there, okay, we have a pendulum that consists of a 500-gram metal ball. What do you need that in? Kilograms. Okay, suspended on a 50-centimeter string. Okay, do you want things in centimeters? You want them in meters. Okay, the ball is pulled horizontally upward. Okay, or so it's pulled horizontally and up a total vertical distance of 10 centimeters. Put that in meters. Okay, and it is then released. At the bottom of the arc, the mechanical energy of the ball was determined to be 0.491 joules. Okay, what is the speed of the ball at the bottom of its arc? Okay, so this one, while mathematically much simpler than the ones we've just done, does require you to really understand what's happening in the pendulum. Okay, so take some time. You're trying to find the speed of the ball at the bottom of the arc. And they tell you how much mechanical energy it has at the bottom of the arc. Okay, so the trick with this one. When it's at the bottom of the arc, it only has what kind of energy? Kinetic. So did they tell you the kinetic energy when they told you the mechanical energy?
Yes.
That's the trick. Okay, that's what makes this question such a simple mathematical question. Okay, all you're going to do is say, all right, this number here equals EK, which equals 1/2 mv squared. And we know at the bottom of the arc, the pendulum can't fall any further. That's where it's moving the fastest and only has kinetic energy. Okay, so if I'm trying to find the speed, I'm just going to divide both sides by half of m and square root, and I'll have v. So v will equal the square root of 0.491 divided by 1/2 times 0.5. So 0.5 times 0.5. Okay. All right, so 0.491, okay, divided by 0.5 times 0.5, and then square root that. Okay, and we got 1.4 meters per second. Okay, quite frankly, that would be a multiple choice question. Okay, because there was only one calculation to do. Okay, there wasn't really any huge amount of work to do on that one. Okay, does everyone follow why that's kind of a good question? Okay. It's not mathematically challenging, but it tests your understanding of the law of conservation of energy and the concept of mechanical energy. Okay, knowing that at the bottom of its swing, okay, a pendulum can only have kinetic energy. Okay. All right, everybody okay with how that one went? All right, we talked about the pendulum already. Skip that, okay. All right, I'd like you to write this one down. It's my horrible chicken scratch, I know, okay? But this is gonna be a typical, like exam level, this would involve the most algebra kind of a conservation of energy question. All right, so we have a sledder, that's a toboggan, not a candy cane, it's a toboggan. Okay, and that's a person sitting on the toboggan. Oh, it moved, it moved. Now they're floating underneath it. Oh no. My beautiful picture. Okay, there we go. All right, so sledder with a mass of 70 kilograms is at a point 30 meters above the bottom of a hill, moving at 1.5 meters per second. How far above the bottom are they when they're moving at 7.5 meters per second? Okay, we're going to assume the hill is frictionless and that no energy is lost. In other words, it is an isolated system and energy is conserved. So, in this question, is there any mention of work, force, distance? No. Okay, then it's not a work energy theorem question, agreed? Plus we already said it's a conservation of energy question, so, okay. So we're gonna say that we're gonna start out with EI equals EF. Our mechanical energy at the top of the hill is the same as our mechanical energy lower down the hill. All right, that means we're gonna say EP initial, so our initial potential plus our initial kinetic equals our final potential plus our final kinetic. Whoop. Okay. Are any of those zero in this situation? No. Okay. We have potential at the beginning because we're 30 meters above the bottom. We have kinetic initial because we're moving at 1.5. Okay. Later we have kinetic because we're moving at 7.5 meters per second, and we're being asked to find the final height, which I would have to assume is not zero, or they wouldn't be asking us to find it. Okay. Everyone all right with my reasoning there? All right, so I can't cancel any of those out. But what I can do is identify that what I'm looking for is part of that term, final potential. So I want to isolate that before I put my formulas in. What do I do with EK final? Subtract it over to the other side, because I'm adding it right now. Okay, so I'm going to have initial potential plus initial kinetic, or mechanical energy, minus my final kinetic energy equals my final potential energy. So I'm saying my mechanical energy minus the kinetic energy should equal my potential. Does that make sense?
Yeah.
Okay. Now I can put in my formulas. All right, so I'm going to say now that m times g times h initial plus 1/2 mv initial squared minus 1/2 mv final squared equals m times g times h final. Okay, I'm trying to get h final by itself. What do I do with m and g? Divide them. Do I need to keep the m's? No. M is in every term. And if something is in every term, it affects every term in exactly the same way, which means it could be 1 or not there at all. Okay? So if you want to, at this point, and I do because I'm like punching in extra numbers, I can cancel off all the m's. If you want to punch in extra numbers, you know the mass is 70 kilograms, so you can leave it in there. Okay? All right, so now I've got that. I just want to get HF by itself, so I just need to divide both sides by G. And I got HF by itself. So when I'm putting in my numbers, I'm going to have 9.81 times 30 meters plus, listening guys, 1/2 times 1.5 squared minus 1/2 times 7.5 squared divided by 9.81. That'll give me my final height. So 9.81 times 30 plus 0.5 times 1.5 squared minus 0.5 times 7.5 squared divided by 9.81. All right, so their final height is 27.2 meters. Why? They only went down 3 meters. Vertically. They would have gone further down the hill than 3 meters. They descended vertically 3 meters. Okay? And remember, the hill is frictionless, so you're going to plow down that hill. Okay, we're going to work on that some more tomorrow.